So remember when we were talking about linear equations, like just single linear equations of first and second order, we talked about the superposition principle. And what this allowed us to do is in this situation where we had a homogeneous equation, we were able to take two solutions and then construct what's called their superposition, which is the physicist way of saying just a linear combination, a constant times the first solution plus a constant times the second solution. And when we construct that new expression, it turns out that that new expression ends up being a solution, again, to the homogeneous linear differential equation. Something like that is true also for linear systems. So I want to make sure that we say that out loud. So I want to talk about superposition. Okay. So the idea is that suppose we have two solutions, x1 of t, and this is a vector. You have to imagine it's an n by 1 vector of functions, and x sub 2 of t. Again, another n by 1 vector, possibly different. Our solutions to the homogeneous, it's got to be homogeneous for this discussion to work, system, which is going to be given by x prime equals p times x, where p is a matrix here, okay? I'm suppressing the of t's. Now, just remember and recall, this from the last video, we talked about how this is what a general system looks like. It's x prime equals p times x plus f. But now that we tag the adjective homogeneous to everything, we know that this f is 0. It just goes away. Okay? So we have x1 and x2 are solutions, meaning that they satisfy this equation for x. When you plug x1 in for x, the derivative of x1 really is this matrix times x. Similarly for x2. Okay? Then, the punchline, any superposition of x1 and x2 is again a solution. Okay? This should be relatively clear, actually, okay? Because let's just think. Suppose that we take, for example, c1 times x1. So a superposition is something that looks like, just to be clear, a superposition is something that looks like c1 times x1 plus c2 times x2. That's a superposition of x1 and x2. Now, let's plug that in to our differential equation. When we have c1 times x1 plus c2 times x2 prime, right? We're going to take the derivative, in other words, of this. That's I'm just putting this superposition into the left-hand side of my my system. But I think it's entirely plausible, isn't it, that because of the rules of derivatives, that this is just c1 times x1 prime plus c2 times x2 prime. That might take a little thought, but hopefully it's something that's you can be convinced of. But on the other hand, this, okay, because x1 satisfies the differential equation, when we take the derivative of x1 prime, okay, that's equal to p times x1. Similarly, x2 prime, because x2 is a solution, is also equal to p times x2. So we can rewrite this equation as c1 times p times x1 without the prime plus c2 times p times x2. These should have hats. Yes. Now, we know that multiplying a matrix by, like when you have a constant mixed up in a matrix product, Okay, that constant can move around wherever it wants to be. All right, so I'm going to move the C1 and the C2 so that they are next to the X1 and the X2. And then I'm going to factor out the P. So I'm going to rewrite this as P times C1X1 plus C2X2. And what this shows is that C1X1, the superposition, plus C2X2 satisfies the differential equation x prime equals px. Okay? Cool. So we have this nice superposition principle at work when we are working with homogeneous systems of differential equations. Nice. Now, the thing is that when we are working with something like x prime equals px, we want to be able to obtain the entire set of solutions, all the solutions, the so-called general solution. So how do we find the general solution to something like x prime equals px? I mean, what we have now is a method. If we have a bunch of solutions, we can combine them together in a superposition to get new solutions. So in particular, we should see now, if in particular we have a bunch of solutions like x1 through xn are solutions, then so is this sort of grand superposition, which looks like C1x1 plus C2x2 all the way up to Cnxn with hats on top of all the x's. Yeah? That should follow from the considerations that we just described. I don't want to go into detail on that. That should be commonsensical. Okay? But that is an important idea. So if we can find, and maybe I should say fact, which I'm just going to shove down your throat, foie gras, yeah. The fact is that the solution, the general solution to x prime equals px, okay, is n-dimensional. In other words, there are n knobs that we can turn on the solution. So this is just a fact that I'm shoving down your throat, okay, and you're swallowing it. Great, thank you. But now knowing this gives us a strategy here, okay? The strategy is to find n solutions which point in different directions. This is not unlike what we did with the second order equations, where we found two different solutions which weren't scalar multiples of one another. They were so-called linearly independent. But now we want n solutions, each of which sort of point in a distinct and unique direction from the others. So what in particular does that mean? So I'm going to write down some words and then I'll sort of elaborate. This gives a strategy to solve x prime equals px. Find n linearly independent solutions. Linear independent geometrically just means that they all kind of point in different directions. But I'm going to define it more precisely. So, definition. If you have a bunch of these functions like x1 through xn, so x1 of t, x2 of t, these are all vectors now. xn of t, these are vectors of functions, remember. They're all time dependent. Are linearly independent. And this is a kind of fancy definition, which geometrically is an encoding of the description I just gave you. They all point in distinct directions in some sense. Are linearly independent if anytime you can have an equation, anytime you have c1 times x1 plus c2 times x2, anytime you can form what a superposition or linear combination, either way you want to call it, anytime you can form a linear combination of these which is equal to the zero vector. So like say you could amalgamate x1 through xn in this kind of equation. This implies that the only way, this implies that these coefficients have to be the stupidest way of doing this, which is that all of the coefficients are zero. Then C1 is equal to C2 is equal to C3 is equal to all the way up to Cn. All of these coefficients have to be zero. That's what it means to be linearly independent. Okay, so if we can find n linearly independent vectors, x1 through xn, which are solutions to x prime equals px, then you can form the superposition, and that will be your n-dimensional solution to your differential equation. Why n-dimensional? Because then you would have these n knobs, c1 through c2 through cn, these n different parameters that you would be able to tweak and turn the values on, change the values on, and you would still have solutions. And there would be no redundancy either, okay? And that's because of the linear independence idea. Just geometrically, okay, because I know it's a challenging concept, this linear independence thing. Here is a picture of three linearly independent vectors in R3, something like this. So like if you have three vectors that look like this, if this is x1 maybe, this is x2, this is x3, these are linearly independent. X1 and x2 sort of lie in a horizontal plane, and x3 points in a completely, entirely different direction, right? Out of the plane in particular. So these are linearly independent. But something that looked like this, if you had, let's say, x1 and then x2, but then x3 was just sitting inside of of the plane containing x1 and x2. So like you have, like here, if you have the x1 and x2 like this, they together kind of span a plane, right? There's a plane's worth of vectors that they're sort of carving out for you in space. And now imagine you have that x3 living in that plane. That's linear dependence. And that's not what we want. Linearly dependent. Okay? Oh, you can't see that. That's linear dependent, right? And that's not what we want. And the reason is because we can express, in this case, we could express x3 as some linear combination of x1 and x2. And that's because x3 lives in the plane that's spanned by x1 and x2. So we could find coefficients which are non-zero of involving x1, x2, and x3, which gives the zero vector. Okay? Now, how can we easily detect if something is linearly independent? Okay, so here's an idea for detecting linear independence. And this is, again, a little bit of a foie gras moment, because I'm not going to fully justify this. You take a linear algebra class to really understand this. The idea for detecting linear independence is you can, if you have x1 through xn, then you can form a matrix, an n by m matrix. And it's going to be, I'm going to denote it capital X. This is going to be the matrix whose columns are x1 through xn. Okay? If the determinant of this matrix is not 0, then you have linear independence. Okay, so let's do an example, okay, and this should make things clearer. So I already talked about this system here. Let's do this one, example. I talked about this example. X prime is equal to y, and y prime is equal to negative x, okay? So in matrix representation, this looks like xy is equal to 0, 1, negative 1, 0 times, oh, sorry, this is times prime, times xy. Okay. And I asserted that the general solution is given by something. I did this in the last video. But I'm going to say it a little bit differently here. I'm going to say that the general, that one solution, x1 of t, is going to be given by sine of t cosine of t. That's one solution. And x sub 2 of t is equal to negative cosine of t sine of t. Now, I'll let you check for yourself that these really are solutions to the differential equation. That is, take the derivative of sine t cosine t, for example. Take the derivative of this. You're going to get a matrix cosine t negative sine t. But that exactly satisfies this condition, or equivalently this condition here. Do you believe it? Hopefully you do. Do I believe it? I do. Totally works. Similarly for this x2. Okay? Now, I claim that x1 and x2 are linearly independent. Can I just write linearly independent for now? Lin ind. Okay. So what I'm going to do is I'm going to form x, big X. I'm going to follow the advice of this thing. And this is going to be a 2 by 2 matrix. It's going to look like sine of t, negative cosine of t, sine of t, and this entry is going to be cosine of t. This entry will be cosine of t. This one will be sine of t. Do you see? I'm just mashing these columns, these x1 and x2 together into a matrix. This is like x1 here in this column, and this is like x2 in this column here. Now, what's the determinant of x? The determinant of x in this case is sine squared of t, so that's the product of the diagonals, minus the product of the off diagonals. So that's minus negative cosine squared, minus negative, that's plus cosine squared of t. And oh my God, that's the Pythagorean identity there. And we know that that's equal to 1. And 1 is not 0. So if you believe this criterion, which I'm shoving down your throat, then you'll believe that these are linearly independent. This shows linearly independent. And then to go even further here, what we can then conclude is that this system, the general solution to this homogeneous system, is C1 times X1 plus C2 times X2. C1 times sine t cosine t plus C2 times negative cosine t sine t. Okay? Every solution, in fact, if you believe, there's a lot that I'm shoving down your throat. A lot of foie gras being produced here. Every solution to this system of differential equations is of this form for some choice of C1 and C2. Okay, that's enough for this one. I'm going to say a little bit more about and begin to say something about how we're going to attack and call and attack and kill these things in a bit more generality in the next one. Okay, see you then.